The following is about chapter 8.5 or 8-5. The main difference between chapters 8.4 and 8.5 is that they're both about testing a claim about a mean. In 8.4, we assume that the population standard deviation is known. In 8.5, we assume that the population standard deviation is not known. The difference is then that in this section we'll be using the t-distribution, and the other difference too that comes in is the determination of the p-value. The p-value, when we use the z-score, is relatively easy to determine when we have tables and the likes, and we don't even have technology. But for t-distribution, to determine the p-value, there's a range of values that you can determine for the p-value, but in your homework assignment, you're asked to specify p-value. So for that, you do need technology. Just a little heads up. Now the book, in example number 2, on page 424, gives you an explanation of how to get a range of the p-value when you use a t-distribution. But again, it is not that straightforward, and it doesn't give you a specific number that is accurate to 2 or 3 decimals as required in your homework. So again, you may want to use technology to determine the p-value, whether that's StatCrunch or a calculator like TI-84 or Inspire, or a lot of different choices that you have, or even an online calculator. So to explain how this all works, I will be using some examples. So let's first talk about notation, and what we'll be using here is x bar. There would be the sample mean, n is equal to sample size, and mu sub x bar is a population mean, and that is a value that we take from the claim in the null hypothesis. Population mean. And as I'm showing you some exercises here on how to answer the questions, you'll see how we apply that. And we are making certain assumptions about the requirements. We assume that the sample is a simple random sample, and that either one or both of these conditions are satisfied. The population is normally distributed, or n is greater than 30. So we assume that these requirements are satisfied in each of the cases. Then our test statistic is equal to the sample mean minus mu x sub bar divided by s divided by the square root of n, where s is the sample standard deviation. Sample standard deviation. And then we use, to find critical values, we use the t-distribution in table A3 with degrees of freedom given as n minus 1. And I will use the table, and so you'll see how that is done. But again, we've done this before for chapter 7, and so this is basically the same thing to find the critical values. The first exercise is about uninterruptible power supply, and there's some statistics from Appendix B. The point is that the normal output voltage is 120 volts, so that means our mu sub x bar is 120 volts, And the standard deviation, the sample standard deviation is 0.31. And there were 40 samples, so n equals 40. And we have a significance level of 0.05, so alpha is equal to 0.05. And the question is, test the claim that the sample is from a population with a mean equal to 120 volts. Okay, so let's write down our hypothesis. And so our null hypothesis is mu is equal to 120. And the alternative hypothesis is that mu is not equal to 120. So we're dealing with a two-tailed distribution here. So here's our t distribution. And so it means in each tail we have 0.025 area or probability on each side. 0.025. Our degrees of freedom, of course, is 39, n minus 1. So degrees of freedom 39. And so let me just show you, using a table right now, how to find our critical value. So we go to 39 in our table, 39, and at 0.025, which is further up here, it is 2.023. So 2.023 is our critical value, 2.023, and minus 2.023 is here. Of course, 0 is here. Okay, so let's compute our test statistic. And our test statistic is equal to t equals our sample mean. Oh, that was 123.59, 123.59. So 123.59, here it is, minus 120, our mu sub x bar, divided by s, our sample standard deviation, 0.31, divided by the square root of n, or the square root of 40. And this test statistic is equal to 73.242. By the way, you want to round this to 3 decimals, typically. Now, what this really means is that our test statistic is more than 73 standard deviations from the mean, and certainly way into the rejection region here. So we will reject the null hypothesis, reject the null hypothesis. In other words, what we can say here is there's not sufficient evidence to support the claim that the mean voltage is equal to 100, or there's sufficient evidence to warrant a rejection of the claim, since we reject the null hypothesis, that the mean voltage amounts to 120 volts. Okay. So, as I mentioned in the beginning, how do we get the p-value? Again, the p-value, you really want to resort to technology. And when you do that, the p-value turns out to be, well, basically 0 if we use technology. In reality, what we do say is p is less than, in the case like that, less than 0.01. Because the p-value is never equal to exactly 0. But that's what technology tells us. So since p is less than alpha, because 0.01 is certainly less than 0.05, again, we reject the null hypothesis. And in summary, we can say there is sufficient evidence to warrant a rejection of the claim that the mean voltage is equal to 120 volts. The next exercise is about the analysis of pennies. Actually, it's about the penny amount on checks. So to analyze an analysis investigating the usefulness of pennies, the cents amounts or cents portions of 100 randomly selected checks are recorded. The sample mean of 23.8 cents and the standard deviation of 32 cents. If the amounts from 0 cents to 99 cents are all equally likely, the mean is expected to be 49.5 cents. Use a 0.01 significance level to test the claim that the sample is from a population with a mean less than 49.5 cents. What does the result suggest about the cents portion of the checks? So let's write down our hypothesis. So the null hypothesis is that the mean is equal to 49.5 cents. And the alternative hypothesis is that the mean is less than 49.5 cents. And then n is equal to 100. That means our degrees of freedom is equal to 99. And our alpha is 0.01. And so our critical value, when we use our tables or technology, either way. So when we use our table, 0.01 for alpha, and then we go down to, well, we don't have 99, but we have 100, so we come up with 2.364. 2.364. Let's see if we can view here. So 2.364. Okay, here we go, 2.364. Okay, so that's our critical value, and it's of course on the left, minus 2.364, since we have a left tail distribution from looking at the alternative hypothesis. So now we compute our test statistic. So our test statistic would be based on our mean of 23.8 volts, 23.8, and cents rather, minus 49.5 cents, divided by the standard deviation of 32 cents, divided by the square root of 100, and that is equal to minus 8.031. So minus more than 8 standard deviations from the mean to the left, and that's certainly in the rejection region, so we reject the null hypothesis based on the test statistic, reject the null hypothesis. Now, when we look up the p-value using technology, because as I mentioned before, that doesn't work out too well when we have the t distribution. The p-value, if we use technology, comes back as 0. But of course, in reality, it's never 0. So we use p less than 0.01. And in other words, the p-value is less than 0.01, less than our level of significance. And so we can make the statement to say that there is sufficient evidence to support the claim that the mean is less than 49.5 cents. And what this suggests is that the cents portion of the check amount are such that the values from 0 cents to 99 cents are not equally likely. Exercise 22 is about speeding, California speeding. A simple random sample of 40 recorded speeds in miles per hour is obtained from cars traveling on a section of Highway 405 in Los Angeles. The sample has a mean of 68.4 miles per hour and a standard deviation of 5.7 miles per hour, and this is based on data from SigAlert. Use a 0.05 significance level to test the claim that the mean speed of all cars is greater than the posted speed limit of 65 miles per hour. So let's write down the data that we have. So we have a sample mean of 68.4 miles per hour, the sample standard deviation of 5.7 miles per hour, our significance level of alpha being 0.05, the sample size is 40, and our mu sub x bar is 65 miles an hour. So our null hypothesis then is that the mean is equal to 65 miles per hour, 65 miles per hour. And the alternative hypothesis is that the mean is greater than 65 miles per hour. So we can use the tables one more time to look up the critical value. So when we go to our t-distribution table for 39 degrees of freedom and at a significance level of 0.05, that turns out to be 1.685. 1.685 right here. This is our critical value. And from the alternative hypothesis, we know we have a right-hand test. So 1.685 is our critical value here. Our test statistic is x bar, our sample mean of 68.4 miles per hour, minus mu sub x bar of 65 miles per hour. And then the sample standard deviation is 5.7 miles per hour divided by the square root of 40. And this value is 3.773. 3.773. So that means we are more than 3 standard deviations above the mean of 0. So in other words, we are certainly in the rejection region, which means we will reject the null hypothesis. Reject the null hypothesis. And if we look up the p-value by using technology, we find that p is less than actually 0.005. So again, now we have set the p-value is less than our alpha. So that again points to p is less than alpha. So that again leads us to reject the null hypothesis. And the conclusion is that there's sufficient evidence to support the claim that the mean speed is greater than 65 miles per hour. So again, in summary, there is sufficient evidence to support the claim that the mean speed is greater than 65 miles per hour. The last example is about the number of English words. A simple random sample of pages from Merriam-Webster Collegiate Dictionary is obtained. Listed below are the numbers of words defined on those pages. Given that this dictionary has 1,459 pages with defined words, the claim that there are more than 70,000 defined words is the same as the claim that the mean number of defined words on a page is greater than 48.0. Use a 0.05 significance level to test the claim that the mean number of defined words on a page is greater than 48.0. What does the result suggest about the claim that there are more than 70,000 defined words in the dictionary? So let's look at the data. And so when we use the existing data here, we find that our sample mean is equal to 53.3 words, and that the sample standard deviation is equal to 15.656. Our alpha level is 0.05. Alpha is 0.05. And n is equal to 10. There are 10 samples. Okay? So then our null hypothesis is that the mean is equal to 48 words. 48 words. And the alternative hypothesis is that the mean is greater than 48 words. The mean is greater than 48 words. So we have a right tail distribution. And so with this area is 0.05. And so n equals 10 means our degrees of freedom is equal to 9. So when we use the table to look up our critical value, we go to 9, and at 0.05 it is 1.833. 1.833. Okay, there we go. Okay, our critical value is 1.833. And when we compute our test statistic, which would be 53.3 minus 48 divided by the sample standard deviation of 15.656 divided by the square root of 10, that is equal to 1.070. So in other words, our test statistic comes in here somewhere. If this is 1.833, here is 1.007, 1.070. So here's 0. So we are not in the rejection region, which tells us to fail to reject the null hypothesis. Fail to reject the null hypothesis. And when we compute the p-value using technology, we find is equal to 0.1561. So that tells us that the p-value is greater than alpha. And again, that leads us to conclude to fail to reject the null hypothesis. So let's state our conclusion, and actually two. First of all, about the rejection, not to reject the null hypothesis. So here we say there's not sufficient evidence to support the claim that the mean number of defined words on a page is greater than 48. But there was also the other question about what it says about the claim that there are more than 70,000 defined words in a dictionary. And here we can also say, for that we can say, there's not enough evidence to support the claim that there are more than 70,000 defined words in the dictionary. So this concludes section 8.5 with these examples, and I wish you all the best of success with your homework and the forthcoming exam.